Well, welcome to another one of my small, funny physics. I wouldn't call it lectures, but just want to present the things I know and try to counteract or give another explanation for some of the claims that have been made out here in the vastness of YouTube space. I made a small paper with the things I hope to get through, and also some basic calculations in order not to waste time on that. I've been actually on my videos, there's been a lot of debate, and I think that's very good. That's actually why I made this video, in order to debate these things. One particular question asked me why I didn't add the tag flat earth debunked. And although that is, you could say, my motive, because as far as I know, the earth is spherical, it's round, and definitely not flat. But I'm not here to in general debunk anything. I'm not here to say you're wrong. I'm just here to present explanations using physics to show that other explanations might be wrong. I can't definitely say that they are wrong. I can just say from my understanding of physics, if it's physics we're discussing, that is, of course, then the explanations are wrong. So that's why I haven't added that tag, that particular tag. Alright, today I would like to go through two topics. The first is Brian Mullin's claims about the Cavendish experiment. I think it's his second video. In general, I think that's fine. And then I will go on to some claims made by another flat earther, the Morgile, I'm not sure how to pronounce that. And then finally, I will go in some general physics discussion, because I've just blabbered out conservation of momentum, for example, but I haven't really sort of shown what it is in real basic physics terms. So that's related to, for example, the helicopter example. Why can the helicopter hover and then follow the earth around? I like to show that, and I have to do it within 50 minutes, so it's gonna be fast. Alright, maybe this one. So the first thing is that Brian Mullin makes some claims about the Cavendish experiment. Now, his second video, he makes a lot of basic calculations. I think it's about weight and so on, and the calculations themselves are fine. That's why I won't be spending so much time on that particular video. What I do want to say is that he has made some unsubstantiated claims or accusations about Cavendish. He sort of speculates, what if Cavendish didn't actually measure this? What if he actually derived it, or sort of things. And we can't really use that for anything. It's nice to speculate. What if the moon was made of brown cheese, or the core of the earth was made of chocolate? That would also be a nice speculation. Then I would certainly like to try to dig my way down to the core. But we can't really use that kind of speculations for anything unless we can substantiate it somehow. And furthermore, he sort of says, I have never seen anyone reproduce this experiment in its original state. No, that's because that would be stupid. It's the same reason that astronomers no longer use photographic plates. Why don't we try to reproduce some picture with a photographic plate? Well, that's because the CDs can do the exact same thing, and much better, because we have a lot of more options to work with. But I've found a page where a simple high school class, sorry, not simple, but a high school class has reproduced this experiment and found G within a reasonable uncertainty. So the experiment has been reproduced many times, and I would like to add that the gravitational constant, which obviously is not a constant because it has changed, but the idea of it is that it's a constant, but we just don't know the right figure yet, is an active field of experimentation still in physics. It's not settled. The only thing that's settled is that we have gravity, that we have a gravitational constant that goes into gravity, but we don't know what the gravitational constant might be. It might be much higher, much lower. But what we have now seems to be reasonable. Be reasonable in comparison to what we can observe. All right. So the second thing I'd like to go into is the TheMorgile. Now he makes some simple claims that if the Earth was round and going around the Sun in a whole year, then how can we see Polaris? Why doesn't that change position? Well, I won't go into the picture that he made, but I'd like to show why we can see Polaris from the Northern Hemisphere, no matter what time of the year it is. And the key question here, the key answer here, is distance. So, in his terms, we'd like to say that Polaris is here, then we have the Earth here, and the Sun is here. So I'll just make the Sun as a dot. So, and that's the northern, that's north up here, that should be an arrow. And then we have the same Earth here at the opposite side. And then they can see Polaris, right? But they can't see Polaris here. Now, why is that wrong? That is wrong because he assumes that Polaris is just outside my backyard, alright? He thinks it's like going to the next city, but it's not. The distance is extremely large, so what he should have been drawing actually was that Polaris is up here, and then we have, and this is going to be very tiny, then we have the solar system down here with the Earth pointing this direction here and the Earth pointing this direction here. And I hope we can agree that no matter what time of year it is, you can see Polaris, but you can't see it from the sun. Sorry, from the south. You can see it from the south, and that is why, as I'm also an amateur astronomer, I have my own little backyard telescope, and that is why I'm particularly happy for being at the North Pole, because it's much easier to align the telescope to the North Pole. All right, so that's the first thing about the TheMorgile's claims, and this is really basically just to say, so it's not really that hard. The other thing he claims is that, well, it's about the centrifugal force. Now I'd like to, centrifugal force, I'd like to make one particular thing very clear. The centrifugal force does not exist in an inertial frame of reference or an inertial system. It is what we call a fictitious force. It doesn't exist. The real force at play is called the centripetal force. But the centrifugal force is sort of what we feel. Not I'm feeling sad, but when you sit in a merry-go-round or something and you're sort of keeping yourself from sliding out, that is because you feel the centrifugal force, but it's still a fictitious force. It's not real. It's not there. So that's from a physics point of view. Point of view. Anyone tried a merry-go-round knows it's there. But his claim is that if we have two persons, this is the Earth, we have the equator here, then we have a little man standing here, and we have a little man standing here. Or it could be the same man just taking a long trip. Alright, so his claim is that the person here going around very, very fast. That is, I can't remember what it is, 900 miles per hour, I think it is, something like that. I think it's about 1600 kilometers per second, something like that. I can't actually remember the figure, but I have another figure here that we can use. But it's just it's fairly fast compared to what we're used to. All right. So his claim is that why don't this person feel almost like being flung out of Earth compared to this person up here who just doesn't almost, let's say he's standing at the exact North Pole and he feels absolutely nothing. Let's try to calculate the centrifugal force in order to see what we're dealing with. Alright? So let's take me for an example. I'm a pretty heavy guy, so my mass is around sorry, not 900 kilograms. 100 kilograms. Alright? So what we use, let's just put the formula up first. The formula for the force of gravity at the equator, for gravity is m times g. That we know. Alright? The centrifugal force, C, is m omega squared times r, where m is the mass of the person, that would be me. Omega squared is what we call the radial velocity. It's basically the normal radial velocity divided by the radius. This comes in radians per second, if we use per second of course, but I've calculated it as radian per second. And the radius is the radius of the Earth, that is what we have here. And omega is sort of the speed around here. Alright? And it's fairly easy to see that this person here feels the full force of omega, and this person up here feels almost nothing. So let's put in the figures. The velocity of the Earth in radians per second is 7.3 times 10 to the minus 5th radians per second, I think it is. Yes. The radius of Earth is 6.30 times 10 to the 6th. Yes, 6 meters. And then we have G. Let's take two G's. We take G's here and G here. Now I haven't looked it up. It's just what I remember from my head. But let's say that the G at the equator, let's call that GE, is equal to 9.82 meters per second squared. And G at the North Pole is around 9.80 meters per second squared. Alright. So I've calculated these things in preparation, so I just put in the numbers. But you can calculate these things by yourself and see that hopefully I'm correct. So what I found is that the force of gravity at the equator is equal to, well, that's easy. That's because I've used easy numbers, 982 newtons. The force of the centrifugal force at the equator is roughly equal to 3.4 newtons. We can use 3, round down. Alright? And the force of gravity at the north is equal to 980 newtons. And of course the force of centrifugal force at north, let's just say, is roughly 0. Something like that. Then it's easy to see that if you round this number down just to be 3, then the force, the difference, let's say that what we experience would be the gravity is in this direction and the centrifugal force is in this direction. Alright? So let's subtract them. So that would mean that these two subtracted would give roughly 979 newtons, and this number here is 980 newtons. So you can see that the real difference here is so extremely small that claiming that this person here should feel like he's being flung out of the earth like water on a tennis ball spinning, and this person here should feel absolutely nothing. It's hilarious. Because the magnitude of the force, the magnitude of the centrifugal force, even on Earth, even spinning with a relatively high speed compared to our daily speeds, it's negligible. We can just ignore it. Alright, I hope I had time to go through one last thing.